Swayam Prabha. Digital India. Educated India.
Good morning and welcome to lecture 38, which is on fluidized bed carburizing process. This is under module 8 of the course that we are discussing environmental degradation of materials and surface engineering. We have to pay attention to this particular adjective, fluidized bed. So what it means essentially is that unlike the previous case where we conceptually had a box and the component was packed inside with a box filled with certain solid charge, which we said the pack, and the pack comprised primarily the charcoal or carbon containing material or coke, and then barium carbonate or one of those carbonate materials which actually can decompose and produce carbon dioxide at high temperature, and maybe some catalyst and some other sand and some other packing material. So entire process was solid state, and which basically was filled up inside the box containing single or multiple such components which were to be carburized. So unlike that situation, here we are dealing with liquid carburizing or liquid bath carburizing. So in this process, we are obviously not only using a different state of matter, liquid state, but also the charge is different. And basically we are dealing with cyanide material, and the very name certainly would convey a very unmistakable message that we are dealing with an extremely dangerous and also which decomposes into sodium cyanamide group of materials, and eventually through certain reaction it produces the barium cyanate material. And the most important thing is that this barium cyanide undergoes decomposition when it comes in contact with ferrous substrates and releases carbon, and that too carbon in the nascent form. So this atomic component. So the process involves, instead of a solid pack or a box, we have a bath, we have heating device through either flame or resistance heating coil or something. So that the salt that we are dealing with, essentially sodium cyanide, that should actually be in the molten state. So this is a salt, it has its own fusion temperature. And once it is in the molten state, then it dissociates into a lower compound, sodium cyanamide, and that releases carbon. So essentially one carbon comes out of this dissociation process. This is more possible at lower temperature, but when we are dealing with slightly higher temperature, then this sodium cyanide can react with barium chloride, another salt present in the charge, and form this cyanamide, and cyanamide in turn can react and dissociate at the iron or steel surface and contribute to nascent carbon for diffusion. So this is the bath composition, and as I said that this is a molten or a liquid bath, and so we have to hold the component inside the bath so that we can enrich the surface or create a case of carbon enriched surface. And this is usually a carbon enrichment process, and obviously will have very low nitrogen content. But in some cases, certain amount of nitrogen dissociation and adsorption at the surface is also possible. So the point of distinction here is the liquid state, the charge that we are dealing with, and the temperature that where we do. one very important point, and that's absolutely not to be missed out at all, is that we have a lid which has to be completely hermetically sealed so that there's no escape. This is absolutely not sodium cyanide, and even inhalation of that vapor can lead to not only it can lead to disaster, instant death. So this is to be distinguished from the other carburizing processes in terms of the character and composition of the case that we produce. The cyanide case is higher in nitrogen and lower in carbon, and the reverse is true when we are doing with the liquid bath process. Okay, so it's essentially a salt bath, and the temperature that we are talking about is slightly lower than the back carburizing treatment, typically about 800 to 900 degrees centigrade. Now, as I already mentioned, and no harm in repeating again, that since we are not dealing with charcoal or coal or coke as the primary charge, but we are dealing with cyanide, so excess decomposition of cyanide actually is to be prevented, and it should not lead to any kind of human or any other casualty. So this is the core reaction, and so this cyanide that we use goes to cyanamide and then releases carbon, and this carbon gets absorbed into the component. Again, this is the temperature difference when we are going to the next strategy of carburizing, which is gas carburizing. So let's remember that PAC is solid state, cyanide bath is liquid state, and in the gaseous state we are dealing with slightly different charge, again primarily methane as the primary source of carbon, and here this is the overall reaction, but release of carbon doesn't happen directly from methane. It goes through a certain decomposition process, but the overall reaction would look somewhat like this. And it is this carbon which comes out in the nascent form and gets adsorbed, diffused and dissolved at the surface. So this component which is suspended in a gaseous environment, here again we have a sealed furnace because we are dealing with the methane, and of course release of methane to the atmosphere is not as dangerous as cyanide, but nevertheless we want to retain certain concentration or potential of carbon enrichment inside the chamber. So this charge is suspended from the top and the lid is closed. We charge methane and methane hydrogen or certain mixture, and then we heat. So these are the heating coils, resistance heating coils, and we go up to a temperature of about 870 to 950, slightly higher than the cyanide bath temperature, and then we carry out the operation for a certain period of time. The case depth typically not necessarily always 3 millimeter, typically about 0.5 to 1 or even 2 millimeter. So on the higher side, and the hardness can be fairly high. But let's also remember that the hardness comes only when we do the quenching to convert the surface to martensite. In fact, we need to discuss about the heat treatment processes involved in this all these operations. So just like in case of liquid bath or cyanide bath treatment, here we are dealing with a higher hydrocarbon, propane, and then we allow this to be dissociated. And during this dissociation process, methane forms. Along with that also we have carbon released, nascent carbon released, and that carbon gets adsorbed to the surface. We could also have a parallel reaction where methane reacts with carbon dioxide, forms carbon monoxide, and carbon monoxide in contact with the iron charge or the steel charge allows dissociation, release of carbon from carbon monoxide and carbon dioxide. So these gaseous byproducts, they escape. So they are not much of any consequence. But since there is a hydrogen evolution, so we have to use a closed lid, closed chamber, and also have the possibility of burning out the gas discharge from this reaction chamber. So carbon gets adsorbed to the surface, and then that's how basically we have carbon enrichment or case formation. We also can have a parallel reaction of again formation of carbon dioxide leading to formation of carbon monoxide, and in turn carbon dioxide can release carbon by way of this kind of a reaction. So the case depth or the carbon enrichment from the surface, so this is the surface, and this is how we are going below the surface. So this is the component, and this is how carbon is diffusing in and is creating a case on all sides with certain depth. And typically in any direction from the surface, let's say in this part, this is how the carbon profile looks like. So it's highest at the surface and gradually decreases. So we have to set our goal that we want, for example, 0.8% enrichment or 0.9% enrichment. Then we are talking about, this is the typical depth, so about 0.3, 0.4 millimeter. But the overall carbon enrichment can go to higher distance or higher depth from the surface. So this is typically for low alloy steel. Here the temperature is slightly higher. We are talking about maintaining certain pressure, but the time required is very small compared to 10 hours, 20 hours of back carburizing, maybe a few hours of, or at least close to an hour or two for liquid carburizing. And here in gas carburizing, it's much smaller. And we can have one of these charge, and what we see is in case of acetylene, which actually decomposes faster and a lower hydrocarbon, the carbon enrichment for the same at the same depth is always higher. So methane, if we use only methane, then that's a very stable hydrocarbon. It doesn't dissociate, so it doesn't make any difference at all. So one has to use essentially these unsaturated hydrocarbons, which will be able to release carbon during dissociation process, and that carbon can get adsorbed onto the surface. We actually, gas carburizing this is the finer form, which is called vacuum carburizing. So essentially, this is the finest process because in all other processes which are done in air, you have always certain amount of concentration of oxygen present in the atmosphere. And that oxygen, we all know that iron is very hungry for oxygen. So because it is likely to form one of these oxides, and which essentially contributes to the so-called scale formation. And this is detrimental. We don't want this, because once you have a scale formed onto the surface of steel, then diffusion of carbon becomes practically impossible, because now you have an impervious and so-called barrier layer of oxide, and this oxide doesn't allow carbon diffusion inside. Also, presence of oxygen will create another difficult situation or disadvantageous condition, whereby carbon from the bulk can actually try to diffuse out, react with oxygen, and form carbon dioxide or carbon monoxide. That means you, instead of carburizing, you end up doing decarburization. So in order to avoid all those, one of the most ensured process would be something like this, where you first evacuate reasonable vacuum, 10 raised to minus 3 to minus 5 millibar pressure, and then backfill with carbon containing gases, say unsaturated hydrocarbons, which will eventually dissociate and give methane, and then we'll get carbon coming out of this. And that carbon gets adsorbed to the surface, and that surface is now case hardened. So when you compare, we have already discussed the three possible approaches: the solid, the gaseous, and the liquid bath processes. So so these processes, and the final one is the vacuum process, which is LPG based. So as we see that they have, certain comparison tells us what. So this is, in all the cases, the mechanism involves diffusion of carbon. In case of liquid bath or cyanide bath processes, I did mention that we possibly may end up getting some dissociation of nitrogen as well. So we end up creating a carbonitrated layer. But in all other cases, essentially it's diffusion of carbon. Temperature, slight variation as we go to, for example, gas carburizing or something. There could be somewhat slightly higher temperature used, but the depth that we are talking about will be higher in case of back carburizing or solid carburizing, because you have very little control over it. Once you charge and heat, carbon diffusion, you cannot stop by pressing of a button. The temperature, you have to take that box out and then cool in air and then break it open and then remove the charge. During all the process, there is some residual temperature, and as temperature is higher than room temperature, the diffusion of carbon continues. The temperature decreases, but not to room temperature instantly. So diffusion continues, and as a result, you have slightly higher case depth in case of back carburizing. Lower in case of gas carburizing, and certainly the lowest in case of cyanide bath or liquid bath carburizing. In vacuum carburizing, you actually can achieve this with a much smaller time period. The case hardness range will be somewhat very similar, depends on what is the time temperature combination, what carbon potential we have used, and so on. The substrates are very similar in all the cases, either carbon steel, plain carbon steel, or low alloy steels, or even high alloy steels, and so on. But now look at the overall process characteristics. As I said, this is difficult to control because temperature or the thermal state is higher than room temperature, and you cannot bring to room temperature very instantly. But this is very low capital investment and is conventional, very easy. You don't require very skilled manpower, so very easy to implement. In case of gas carburizing, you have a better control over the case depth, and this is ideal for continuous operation, which is not possible for liquid bath or back carburizing, which are batch processes. So if it's a gaseous atmosphere, so let's say this is the furnace and you have a conveyor belt through which your samples is charged and is allowed to be retained inside the furnace for a certain period of time at a given temperature, and then is withdrawn from the other side. So during this residence time, the component goes through a thermal cycle and gets carburized and then come out. So this can be a continuous process. This is the only carburizing process, the gas carburizing, which can be a continuous process. So that's a big advantage. You can also do a very precise gas control, but it can lead to certain danger if the hydrogen released is not actually removed in time, or some other exothermic gas mixture combination can evolve. Liquid carburizing is faster and also is more precise, but the biggest danger comes from during the operation. You have to prevent any escape of cyanide gas or cyanamide gas or spillover from the tank, and also it's highly corrosive salt, so maintenance of the tank becomes another major problem. In fact, in most of the cases, this is no longer practiced, practically banned in some of the cases, but actually offers a very nice metallurgical process, an interesting metallurgical process. In case of vacuum carburizing process, we have an excellent process control. We get bright parts because, as I told you, that there is very little gas oxygen entry into the chamber or oxygen presence in the chamber, which means I have very good bright surface, no oxidation, no tarnishing, and is also even faster than gas carburizing. But on the negative side, the capital cost is higher because you have to maintain the furnace, maintain the chamber at a certain level of vacuum. before you backfill. So this is typically the hardness distribution of the stock after carburizing. So this is depth. So again, let's say this is the specimen we are talking about. This is the case that we have created, and this is the depth that we are talking about. So from the surface into the inside, this is how the depth varies, the hardness varies with depth, and as we can see that up to a certain depth we maintain reasonably high hardness. The hardness can be very large. We don't necessarily need such very high hardness. This is typically in case of vacuum carburizing, but we also can have fairly good hardness maintained depending on time temperature combination. The case depth as a function of time will vary depending on temperature. So as the temperature goes to higher level, the case depth is higher for the same period of time, for the same length of time. So this is liquid carburizing in case of a particular stainless steel, which for various practical purposes is actually subjected to carburizing treatment. And when we do that, we also end up getting higher amount of austenite on the surface because of carbon enrichment. But this oxide film is something which is an aftermath, which probably is created because of exposure to air. Typically, this is how the hardness varies with depth, we have already seen, and this is how again the depth actually varies with time. Now, we have to spend a few minutes here to understand the implications of all these, starting from pack carburizing to liquid bath carburizing to gas carburizing and even vacuum carburizing. In all these cases, what is that we are trying to do? So first thing is that we are starting with a material which is low in carbon, 0.2% or less. So mild steel, lower strength, higher ductility. Most important thing, has higher toughness, so it can absorb energy. So be it for a rotating part or something which is undergoing reciprocating motion or something, if there is a change in stress cycle, then it certainly needs, or sudden application of high load, then it should be able to withstand that amount of mechanical stress. So we require a core, and 90% at least of the component is soft. So the 90% of the component should actually, initially we are starting with the entire 0.2% carbon steel, mild steel or low carbon, low alloy steel, and the composition is same all throughout. Then we are just going to enrich only about 5 to 10% of the surface area with carbon and leave the remaining 90-95% unaffected, same composition. So the core, which is 90 to 95%, retains this low carbon region, whereas the surface or the case gets enriched to about 0.8, 0.9 or 1% carbon. So this becomes the surface. So we are dealing with, initially we are starting with the same material, and then we create a differential composition across the thickness. Surface enriched with carbon, core leaner in carbon. The objective is to create such martensitic aggregate in the surface region. So in order to do that, we can't convert from at room temperature. So we have to heat, and we heat such a way that we heat to a temperature above austenitizing temperature, typically AC3 for the hypoeutectoid range and AC1 for hypereutectoid composition, and then we quench. When we quench, we have to ensure that we are quenching at a rate faster than the critical cooling rate, so that we can avoid the nose. So this is important thing. And once we do that, then we end up with this martensitic aggregate. And this martensitic aggregate, please remember, not only has martensite, but may also retain some retained austenite. The lower the amount, the better it is. But not 100% martensite is practically impossible because of variation of depth and the corresponding cooling rate variation. So typically we can go through various kinds of carburizing cycles, which essentially is to expose to high temperature above AC3 primarily. in solid state, with liquid, in contact with a liquid bath or a molten salt bath, or in contact with a gaseous environment, or gaseous environment backfilled after creation of vacuum. In all these cases, the surface is exposed to highly enriched or carbon enriched environment, and that's where carbon comes in. So that process requires diffusion, and that's why we have to maintain high temperature. And we necessarily have to go to austenitic region, because austenite has the highest carbon dissolution or absorption capacity. So carbon solubility is about 2.11% when it is in austenite region. Compared to that, the ferrite has only 0.025 or less. So it is for this and two reasons. One, that the carbon diffusion rate is higher because temperature is higher at high temperature, so we have to go to austenitic region. And number two is that the capacity to dissolve carbon is much higher in the austenitic region. So that is why all carburizing treatments, be it solid, liquid or gaseous state, has to necessarily go to the temperature above AC3 or in austenitic loop, pure single phase austenitic loop. So this is how we actually enrich, and then so during the enrichment process we have to heat, and this typically is your AC3 and this is AC1. So we have to necessarily heat to above AC3 in all these various thermal cycles which are possible. Now, after we have carburized, particularly let's say a pack carburized component, we have to, this is carbon enriched all right, but not yet martensite. So how do I arrive at this martensitic surface or martensite enriched surface? Then I again have to reheat the surface and then quench. But if I do that, then this is going to create again a situation where I am subjecting the component to higher thermal shock, and also possibly something that I don't need, because the core is at a lower carbon content. And for 0.2%, if you want to go to austenite and quench, you may end up getting martensite, but that martensite will have very low carbon content and is inadequate to give me any wear resistance. And that's not desired either. That's not our target. So I would rather go for one of these treatments where, for example, I first heat the surface, the entire block, and then cool in air, so that I do this kind of a normalizing treatment. So I create a grain refined core, and then I do again another heating, not above AC3 but just above AC1, and then quench. Because this is where, this is for the case or the surface, because the surface doesn't need this higher temperature. Even just above AC1 is sufficient, and when I heat above AC1, I'm already in austenitic region, and now when I quench fast like this, then I can convert that austenite to martensite. So 3, 4, 5 is good enough a cycle, but a combination of cycle for converting the surface to martensite and also ensuring normalized or fine-grained structure of the core. So this is possible through this kind of, this is a typical single-step carburizing, and this is a two-stage carburizing process, heat treatment process after carburizing. So we have to understand that the conversion of martensite, a conversion of austenite to martensite, requires a special heat treatment after carburizing. In case of gas carburizing or even liquid bath carburizing, it's easier to withdraw and then charge to quenching bath. But since we have closed chamber, in all these processes are batch processes. So first part is only carbon enrichment, and the next part is the heat treatment, which essentially is the cycle required for conversion of austenite to martensite. And this is how we can ensure a typical predominantly martensitic surface in the case or the surface region. So we have to ask ourselves some of these questions, the differences in terms of solid and molten bath or gaseous state. What are the hazards involved? What are the precautions required? What are the process parameters? How is vacuum carburizing different than solid and liquid state carburizing? How can we increase the kinetics either by increasing the temperature or mode time or higher carbon potential? Why vacuum carburizing is more precise and faster? Because we have a better process control. This is still a very popular case carburizing because it's age-old and is very well understood and requires very ordinary skill sets. And it is only exposed or only applicable to steel because martensite that we are talking about is a tetragonal martensite which can only form from carbon enriched or carbon solid solution, carbon dissolved solid solution in iron. That means we have to go to austenitic range and then quench fast so that we can convert the austenite to martensite. So this is typically possible in carbon steel and not just alloy steel with no carbon in it, or certainly not applicable to non-ferrous metals. Thank you very much for your attention.